Good evening to all. It gives me immense pleasure to introduce the profile of our distinguished speaker today. Dr. Mamila Ravishankar is a renowned professor in mechanical engineering at IIT Tirupati with over 13 years of experience. He holds BTech degree from Sri Venkateswara University Tirupati, MTech and PhD from IIT Kharagpur. His research focuses on nano finishing, micro nano manufacturing, sustainable manufacturing, precision 3D printing, and related areas. Dr. Shankar has published extensively with over 80 international journal papers, 150 conference papers, 10 patents, and 5 edited books. He has guided 35 students and secured significant funding 6 crore rupees as principal investigator and 160 crore rupees as co-principal investigator from esteemed organizations. His accolades include the Institution of Engineers India Young Engineers Award in year of 2015, Indian Society for Advancement in Material and Process Engineering Award in the year of 2011, and Institute Blues Outstanding Sport Personality of IIT Kanpur in the year of 2009. It's now time to listen to the wisdom and insights of Dr. Ravi Shankar. The session is all yours. Thank you very much.
So I'm going to talk on simple to complex features, but I concentrate because this is for semiconductor applications and so on. So I would like to talk slightly on semiconductors that we try to work on. So we work into the area of micro machining and nano finishing group, materials, additive manufacturing and smart manufacturing. Sustainable micro machining group, because why I'm talking about sustainable machining group is preparation of semiconductors doesn't mean that you can make all the things. Am I right? So semiconductors require a lot of cooling. That is evident from your mobiles. You see, mobiles will always heat up. When you heat up, what the thing is that there will be a cooling fluid will be there, and this cooling will be circulated in the microfluidic channels. That is most important in a semiconductor industry. The semiconductor materials, how far it is important, the same thing, the cooling channels, cooling materials, those are also important. I will just brief you, like micro channels that we can cut with lasers, we can cut with various other sources for nuclear applications and so on. This is a machine. This is not the exact machine that we have. This is DT100, which is a older machine. What we have is DT100i, which is an intelligent machine where we have micro turning, micro milling, micro EDM, micro drilling, micro EDM drilling, micro wire EDM, micro electric discharge grinding, micro die sinking EDM. Apart from it, micro laser, and we have another one attachment specialized for ceramic applications like semiconductors, that I will show you in the upcoming slides. That attachment is called simultaneous electric discharge chemical machining. It is a combination of EDM plus ECM, which you can see. So this is how micro turning will do basically for making the electrodes of 30 microns, 50 microns. So you may be thinking how this is relevant to semiconductor applications. In semiconductor applications, for example, I want to make some channels for cooling fluids and other things. That too are any fine elements that I need to manufacture. So those things, so what I require is I need to make the surface area more. If I want to make more surface area, I need to make more and more amount of micro components. For example, the fins. These fins, as many as fins if you can manufacture, you can dissipate the heat. And that too, you have to manufacture on a material called OHFC. So OHFC copper, I don't know how many of you are well aware of OHFC copper. OHFC copper means oxygen free high thermal conductivity. OHFT, I think some. Okay. Okay, these type of materials we manufacture, and this will go on directly onto the top side of the chip. Whenever the chip heats up, this oxygen free high thermal conductivity material will take the heat and dissipate. That's how the cooling of your mobiles will happen. That for that applications, this is one of the beautiful process. Now you can see here, these are the fins that you can see here, microfins and micropillars. This has multiple applications. One, you can dissipate the heat. This directly go and sit on the semiconductor chips, and you can dissipate the heat. At the same time, similar to it, if you are going to make an array of the surgical pin, these pin diameters will be very, very less, like 10 microns or something. This will go and act as a drug delivery systems, dye for drug delivery systems. So array of pins, either you can use for semiconductor applications, either you can use for biomedical applications. Now, what is the beauty of this? What is the beauty of this one is, if you are going ahead with a combination of semiconductors along with the biomedical, you can put these, for example, this particular thing that you can use as a die, where you can make a I mean to say silicone mold. From the silicone mold, you can make the another one where you can have a flexible biomedical point to the care drug delivery systems. I don't know how many of you understood. The function is like that. You have array of metallic arrays that you can see here, my cursor, pillars. On top of it, you just pour silicone, I mean to say PDMS and other things, hardener and other things. What will happen? You get a negative replica. So now you got the all the vacancies. Now in that, what you do is you put a polymer, biopolymer oriented drug delivery system. You just put. So what will happen? You will get similar to this type of pillars, where you can use for point care drug delivery. Now, since it is can be a polymer, you can fix on a flexible electronics, such as, for example, if you have watch, I nowadays many people are wearing the smartwatch. You can put on the beneath side of the thing, and which has a controlled by the chip, so that what will happen, point care drug delivery will happen with respect to time. So that is the beauty about it. The second one, you can make lot of microgears, which I am not going to talk much. However, you see here two SEM images are there and two 3D profiles are there. So if you see here, the basic thing that you can see is, first one, what predominantly all people use. This is same image, and the bottom one. So what is this shows? This is micro EDM process on a metallic material. The second one is simultaneous electric discharge chemical machining. This is the second one. You see how smooth is this? This will be clearly explained in the next slide. You see case number 1 on a semiconductor material. This is purely I'm explaining on a semiconductor material. So I want to make a pocket. I want to make a pocket on it, on a semiconductor material, such as silicon. So what is the thing that you can do? One, being a semiconductor, it has certain properties of electrical conductivity because it is not purely the insulator or something. In that circumstances, the surface roughness that you are going to get is this. In other case, simultaneous electrical discharge chemical milling or machining, because the tool is rotating, that's why it is called as milling process. So you can get a very, very smooth surface. Now you see the difference here on a semiconductor material. I am not talking about any other material because your particular process is on semiconductors. So you see the red line. Red line is the surface roughness that is measured from micro EDM process, electrical discharge machining process. 142 nanometers is the surface roughness. The same input conditions with respect to simultaneous EDM plus ECM, simultaneous electric discharge chemical machining, will give 22 nanometers. Okay. Now, what is can you do? So, being IAT, this is a commercial attachment in our micro machining center. Okay. And this particular attachment cost around 70 to 80 lakhs only an attachment. It is not a complete machine. Complete machine cost us almost all 4 crores. 4 crores, or I mean, say when we purchased it was 3 point plus crores. Okay. So currently it may be charging like that. So only one attachment, that is a beautiful attachment that can be done on semiconductors and conductors. These type of beautiful structures along with a good surface finish you can achieve. So those people who want to work on to this type of areas, they can utilize IIT Tirupati. It is there in my lab, and I am sure this type of commercial simultaneous EDM and ECM in one go is not at all there, not more than 2 to 3 places across India. So I am welcoming you all if you want to use this particular beautiful science oriented where you can get very good publications, very good high rank things. Once you do on commercial system, so you can do wonders. You can do on titanium, you can do on Inconel, you can do on anything. At the same time, you can do on semiconductors also, like silicon, doped silicon. So this is the biggest advantage. We are neighboring to each other because you may be just away by 6 to 7 hours. You can utilize this particular facility. Okay. Why I'm saying this particular facility is this is commercial systems in India. IIT Tirupati is one of those which has. None of the IITs, most of the IITs may not have the commercial things. They may have their laboratory oriented, which so commercial is a better version. So now coming, so in the previous one, nano machining is also happening, nano finishing is also happening. Otherwise, micro machining you can do and nano finishing you can do in a simultaneously in this one. So when it comes to completely nano finishing, okay, of semiconductor materials, you can see here, objective is to finish mirrors, lens that can be made on one of the materials is zero door. I don't know many of you are well aware of ceramics like zero door. See the zero door. Zero means anyhow you know it is zero. It is one type of semiconductor materials or lens materials. Lens materials which thermal diffusivity will be approximately zero. That means, thermal coefficient of expansion is approximately zero. So what is the beauty of it? So we send a lot of electronic components across the planets. For example, if I want to send on moon, if I want to send on Mars rover is there. For example, when you send into the Mars rover or when you send into the moon or any other planet, what is happens once it lands, the equipment will come out, the satellite will come out and start taking the images. Okay, when it start taking the images, what is the biggest thing that you have to understand? What is the biggest thing that you have to understand is my lens that I manufactured in India or in the world should not change its focal point. That means the temperatures in the earth, temperatures in the Mars, temperatures on the moon will be completely different. In that circumstances, one should understand that thermal coefficient of expansion of these materials should be zero. If it is not zero, what will happen? Your focal point will change. And you know, you see normally when you take a camera images, always you need to point, you need to put on which location you want. If the focal position will change, what will happen? You will get a blur images. As simple as that. For that purposes, and semiconductor applications, silicon applications, these all applications, when you send there, you need to have to understand those particular things. Okay, so the first process normally one can use is magnetorheological finishing process. So magnetorheological finishing process, I am anyhow. So magnetorheological finishing process, if you see here, I am pumping the, I don't know whether I have a video here. Just I'm looking for a video basically. If the video is there, yeah, you can see here, I will come back. So liquid I am sending, I am applying the magnetic field and these brown ones are forming chains. You see the liquid I am sending. When this is randomly oriented, when I apply a magnetic field, all are aligned properly. Brown ones are CIP particles, iron particles, and purple ones that you are seeing is abrasive particles. Now, when it forms a flexible magnetic chain, the lens will come and finishing will take place. Now I am going back to make you to understand better. The same thing that you have seen here, I am pumping through the nozzle. I have an electromagnet. When it comes here, it will become a solid or semi-solid. Liquid become a semi-solid and you apply a silicon lens or any type of lens, the polishing will take place. That you can see here, liquid is flowing and when it touches to the flexible grinding wheel, this is forming a strip basically. That strip is because of magnetic. So now why it is forming the strip? Why it is forming the strip is it has three materials in it. One, a continuous phase, silicone oil. Second, two discontinuous phases. One is CIP particles, which are nothing but carbonyl iron particles. That means 99% pure iron particles. Another one is abrasive particles. Now you are mixing all these things and you are sending by a nozzle. When it reaches to the electromagnet, being electromagnet, it magnetizes. When it magnetizes, what will happen? When you apply a magnetic field B, magnetic field intensity, like 0.25 Tesla, 0.5 Tesla, 1 Tesla or something. Normally, magnetic field intensity can measure in terms of Tesla. So now if you understand this, what will happen? Coming back to the fundamentals of our grinding process, because it looks like a grinding wheel. So I have abrasive type, abrasive size, grade of abrasive wheel, structure of abrasive wheel, at the same time bonding material. So abrasive type, you can use diamond, cubic boron nitride, alumina, silicon carbide, boron carbide, whatever. Abrasive size, you can use coarse, larger size, medium, fine, very fine, super fine, whatever may be. Grade, most important grade and structure that you have to understand here. specifically grade. Grade means what? How firmly the abrasive particle is held by the bonding material. So now, what is the bonding material here? The bonding material is CIP particles along with the silicon fluid. So when I am applying 0.25 Tesla, it is loosely bonded because the magnetic field intensity is pretty low. When I am applying zero point 0.5 to zero point 0.6, it is medium. In case of 1 Tesla or more than 1 Tesla, you have a hard grade. That means that my CAP particles are having more strength because you are giving strength from the magnetic field. In that circumstances, abrasive particle held very tightly. So now depend on my initial surface roughness value. For example, my initial surface roughness is 1 micron. I want to get it to like 10 nanometers. So initially, I play with a magnetic field here and I can make it approximately, preferably like I can use 1 Tesla so that I do a rough cut. Then after 10 minutes or 15 minutes, I can go for medium Tesla and then fine Tesla. So that what will happen? In the same grinding wheel, I can make 3 grades, which is not possible in conventional grinding process. In a conventional grinding process, if I want soft wheel, I have to purchase independently. If I have a medium, I have to purchase independently. If I want a hard wheel, I want to purchase separately. But here you can have the flexibility in terms of making this by changing the electromagnetic field. Okay, now structure you can have, if you have abrasive particles less number, so obviously you can go for so open structure, and if you can go for high, you can go for dense structure, and bonding material here is CIP particles and so on. Now you can see which type of lenses that you want: 3D lenses, 2D lenses, concave lenses, so these type of lenses. Semiconductor lenses, I mean say semiconductor materials, you can use for the same thing. Very good works for brittle materials like silicon, silicon carbide. Nowadays, people are talking about silicon carbide mirrors. Silicon carbide is coming as a very, very good alternative for semiconductor applications and so on. In some of the applications, silicon nitride is also coming up in a great way for some of the radome applications where you take the signals and other things. These are various applications where you can see here lightweight materials. Then BK7 is one of the mirror. FS aspherical mirrors are there. So this is, if you see here, these mirrors need to be polished properly. Small mirrors to big mirrors and sapphire, lightweight silicon carbide mirrors and other things. These are all very, very much required. Currently, semiconductor means you have only one illusion, that is silicon, so you may have to change your perspective as you move on. This is one of the MRS setup that we have fabricated on a milling center, CNC milling machine. And this is CNC milling machine where this attachment has been removed, tool master has been removed, and we have fabricated in our laboratory at IIT Kanpur, here where I am currently. I am not in IIT Tirupati, for I just came to IIT Kanpur. I am very happy in my one of the home institutes, that is IIT Kanpur. So this attachment, if I magnify it and I will show you, this look like this. If you see here, I have a pump where I am sending where we are where the liquid is coming here, and this is a perspex based acrylic based grinding wheel. In between that you have a electromagnet. Once the liquid falls, this is forms like this. This is called flexible magnetic abrasive brush. When you see a flexible magnetic abrasive brush, this is going to shear when you are going to rotate it. Okay, so shearing of this one will make a very good polishing solutions. So this is how the schematic diagram also look like, because whenever you have a setup, first and foremost is you have to make a schematic where you want to make wheel, where you want to make the suction pump, where you want to make the releasing pump, and how MRF conditioner can be maintained and so on. These are all the things you need to do this one, then you need to design it. So now the mechanism of material removal. If you see here, the mechanism of material removal that you can see clearly. So this is the animation which I am not going to talk much. So this is how the finishing takes place. Stages. I have a surface peak. When my abrasive particle approaches, what will happen? The magnetic field holds the CIP particles. These are all called CIP particles. Now this will support and move it. When it move it, what will happen? Microchipping action will take place. This microchipping action, this is for one particular peak. Similarly, you may have as many as peaks as possible. That's why you try to do the finishing action. Sometimes your results may not be accurate as you expect because of some of the practical problems. If you see here, I have an abrasive particle, I am finishing it. When I start finishing it, what will happen is my particles which are sheared will go and fall inside the valleys. If you measure the surface roughness, that means that it will give you a very low surface roughness because your chips are inside. So when you still polish it, what will happen? There is a chance that this loaded particles will dislodge, giving rise to a larger roughness value. So that means that the surface roughness increased, which is a good for us. After that, it is decrease. I mean, say decrease, then it will increase, and so on. So you should understand what is the science behind it for that purpose and other things. Okay. Anyhow, this is the thing that we have polished: knee implants, parabolic mirrors. Now, for example, if you see here, these are the MRF capabilities to finish ceramics as well as metals. Another one that we have is convex and concave shapes by ball end. The mechanism is approximately same. Instead of going for a wheel type, we are going for a ball type. So here the magnetic field is like this, and where you are sending a liquid and electromagnets are, these are the electromagnets, and the finishing action will take place. Now you can see how the finishing action will take place on the workpiece materials and other things. So now we have for semiconductors. So this particular workshop is mostly for semiconductor applications. Because of that, this is a practical example of semiconductor that you are going to see here. So this is a silicon blank. Normally silicon blanks will get in terms of a cylindrical silicon blanks. Once you get a cylindrical silicon blank subjected to doping, its electrical conductivity, you can cut using iridium process. If you have a very sophisticated iridium. Why I said sophisticated iridium is IIT Tirupati, again we have a sophisticated iridium which worth about 80 lakhs or 1 crore, nearly 1 crore maybe. Okay, this is from Agile Charmilis, which is a Switzerland oriented machine where you can cut precisely any particular material that is electrically conductive. So these semiconductors are cut by diamond saws, or they can cut by abrasive saws, or sometimes you can also cut by iridium subjected to their doping and electrical conductivity. So when you cut, what will happen? The surface look like this. It's very, very rough. And these rough surfaces you cannot use. So these surfaces need to be modified like this. for electronic packaging applications. So I don't know how many of you know electronic packaging. When I heard the first time this electronic packaging word, somewhere around 2003, 2005, such time, I was thinking electronic packaging means when you get an Amazon parcel, so that parcel where you get a mobile, electronic goods, how they will pack and send, this is called electronic packaging. Later, I understood that is not electronic packaging. Electronic packaging means if you open, whenever your mobile is get repaired, what do? You open and you get start repaired by the repairing person. When you stand nearby him, you can see lot of electronic components and other components are lying there. So proper arrangement within the space of mobile is called electronic packaging. Okay, so I was telling you about micro machining at the early stages. So micro machining is one of the so advantageous thing to make your telephones into mobiles. For example, in olden days, people were using telephone booths for telephone applications and other things. The same telephone came into your hand with a small mobile. Okay, so this small mobile is possible because of miniaturization. That means that making micro components which worth of the same capabilities which are there in the telephone. The size of the component is reducing and efficiency of the component is increasing, but the same time the component size is decreasing. That is the beauty about it. Now, how we can convert this into this, that you can see here. Okay, so this is the surfaces of semiconductor. Okay, so how do we do that? Mechanism I have not written here. Just I would like to tell you that this particular mechanism, we do have two technologies here. Okay, because of the confidentiality and other things, we may not have put because it is recording and other things. So one is oil-based MR fluids, another one is water-based MR fluids. Okay, in semiconductors like silicon, what we try to do is we try to put water-based fluids. So when you have a water-based H2O based, silicon have an affinity towards that one and forms a interfacial layer. So this particular technology is called chemomechanical magnetorheological finishing. So now, what is this chemomechanical magnetorheological finishing? You know already magnetorheological finishing. Now, when I am talking about chemomechanical, so chemo means chemical or chemistry. Mechanical means mechanical operation. So what, whenever I want to have a component like this, for example, initial surface roughness is this. On this, what I will do, I will use a CIP particles plus abrasive particles plus water-based fluid. In that circumstances, what will happen? It is not about water alone. You can use glycerine for not agglomerating the particles. We can use other things also. So when we are using all these things, what will happen? There are the mechanism that will happen in CMP, chemomechanical polishing process. So the same thing we are adopting here, how we are adapting is, once you apply this particular finishing process, water will interact with respect to silicon and makes the passivation layer on the top. Now here, please listen carefully. I have three systems here. One is workpiece, another one is abrasive slurry, the third one is my magnetic fields, okay, or abrasive particles. So abrasive particle workpiece hardness is H1, abrasive particle hardness is H2. Assume that H1 and H2 are approximately same. For example, I am using silicon carbide. I might say not so because we require some chemical affinity. I take silicon as workpiece material. I have a medium. I have silicon carbide as or alumina, which is a lowest hardness value among all the abrasive particles. So alumina. So I am going to put when there is a chemical reaction, when the medium will react, what will happen? So this surface will passivate and the passivation layer hardness will become H3. H3 will be a soft layer. When I am applying certain pressure, what will happen? The passivation layer will go out, leaving the famous silicon surface. That silicon surfaces that you can see here, what how beautifully the surface look like, that is evident from when you put a sensor on top of it. Okay, so this is about my chemical chemomechanical magnetoelectrical finishing process for silicon surfaces and silicon wafers. The surface roughness that we have achieved is 10 Armstrongs. Okay, so this is a beautiful process when you want to measure, make on a flat surfaces and so on. Okay, so here ends my silicon based samples. What I mean to say is MRF process, magnetorheological finishing process, predominantly work for flat surfaces because magnetic field has a intensity. For example, on a flat surface, you can maintain magnetic field intensity uniformly, but at the same time, if you want to maintain on a curvature, what will happen? Field intensity will fluctuate. Okay, so here ends my semiconductor oriented finishing of surfaces and so on. So now I completed my semiconductor oriented one. So this is a deterministic finishing process for flat surfaces, concave surfaces and convex surfaces. For example, if I have complex surfaces with like additive manufacturing, this type of surfaces. For example, with respect to copper, this is a copper sample. If I want to make this conformable cooling channels and so on, roughness is a very big challenge. Okay, so the lot of problems are there. These are the lot of problems: deballing, roughness, waviness, lustrous, microstructure, flatness, maximum peak to minimum valley, compressed residue versus and so on. So we can also do polishing of these things. So half an hour means I will take another half an hour where I can also include the. So this is the first thing. If you have a any type of surfaces like copper surfaces which you need to make for semiconductor application for cooling or silicon blanks, and these are all the things are chemically affiliated ones. For that purpose we can develop the chemicals for polishing, and these are the structures that we have that are polished by chemical route, and then we can have the electrochemical workstation. Electrochemical workstation, we have rinsing, cleaning, then electrochemical reaction, one rinsing, electrochemical reaction, two, lot of things that we can work on to the electrically conductive top-notch surfaces and so on. So then we have a process called electrochemical plasma polishing, which is a better process for lustrous and other things. Okay, so this is very good for making very shiny samples. For example, this is my initial surface, so you can make such shiny surfaces and so on. So these are the one of the examples of this particular process. So now the question is why you require on this much surface roughness. So this much surface roughness is required because of aesthetic appeal, and quality maintenance and so on. For example, if you see here, SWR heads are there. This is a head and this is also a head. So roughness value is approximately same. The problem here is that the shining ability, the shining is very high on this one. So whenever the customer goes to the shop because of this aesthetic appeal, they will purchase more of very good shining surfaces. So we are going to finish the conformable cooling channels. So these type of conformable cooling channels can be there in die and mold industry. At the same time, these type of molds will be there in in case of in case of semiconductor cooling applications also, or any other cooling applications. So, what are the channels? These are the very, very complex channels. It is coming here, going there, coming here. It is not straight away channels. It has certain curvatures and so on. So, to make this one, we also make the semi-solid based cutting tools, that is here. And how it works, you just watch. You can see here how we can polish the veins of additive manufactured features using low viscous medium to high viscous medium, or this type of applications. Okay, so that you can see before and after finishing, and this is the technology behind it, which we have patented almost most of the technologies. And this particular medium, what you are seeing is this one. So commercially this particular medium is about 2 lakhs to 2.5 lakhs per kg, which is not available in India because of the defense and aerospace oriented things. However, we provide that to all the Indian organizations who are in touch with us, around to 25,000 to 36,000 range, almost all 10 times less per kg we always can see. And these type of things will be polishing very, very complex surfaces, because to understand the efficiency of the particular process, we try to use the flat surfaces. From flat surfaces, then one can go to turbine blades and so on. So you can see aerospace engine components, most of the engine components and so on. So this is the one, as I am not eligible to show you. So the defense samples, these are the finishing samples that one can finish. Again, these are the samples that in collaboration with some of the industries that we try to polish SWR heads and so on. Okay. So as I said, Rome is not built in a day. So this particular work we have started, I mean, say our research group has started under the guidance of Professor V.K. Jain at IIT Kanpur in 1996. So by 2000, we able to make a commercial system, and we are finishing now the commercial components and so on. This is how the machine look like, this the interior part, as well as you can see how the exterior part and so on. This is the front view as well as the side view of our machine that we fabricate. Okay, so that no, this is complete in HMI machine. It's a smart machine. Only loading and unloading is to be done. Rest all the things it can do. You see here, HMI is there. Human machine interfacing is there, where I can feed how many cycles are required, what is the pressure required, and I can also give what is the temperature that I want to maintain the medium, because it has a certain system. If the medium temperature is rising, what it can do is it can send the cool fluids to cool the fluid chambers, and that's how it makes lot of smartness. It can measure the forces, it can measure the temperatures, and it can display on the human machine systems. Okay. So these are the facilities that are available at IIT Tirupati. So, so you can see here. Okay. So these are, you can see here, this is the abrasive flow finishing system that I have. And the second one is 8-axis laser micro machining system that you can see here. And I was telling about micro machining center that we have, which we procured around like 3 plus crores. This is another DT100i, which is an intelligent machine that we try to work on micro milling, micro drilling, and it has lot of sophisticated facilities. And being Anantapur or neighboring places, those people can utilize at minimal price. Okay, we don't charge much because being a government organization. Next one is drag finishing system. Next one is 5-axis complex surfaces finishing. And then we have a rheometer, which I have not talked about much things, where you might have seen the medium where you were flowing, it is stretching, it is breaking. So the rheological properties are completely unique. In that circumstances, the signs of flow and deformation you can measure using a rheometer. The second one, the orange one that you are seeing, is a 3D bioprinter basically. If I want to print artificial skin, for example, I want to print your skin, I need to take your cells, then I can imbibe into the extracellular matrix and give the nutrients, and it will grow. Then I need to take the image from your side and I can print it. Any type of organisms that cells, we can print it. Next one is Bruker contour, which is a 3D surface profilometer. And the next one is what is the big thing that we have is filament maker, 3D filament maker as per the customs. Nowadays, people are doing a lot of PhDs. They are coming with PLA, with copper particles. So you can get in the market PLA film, ABS film, filaments and other things. But when you want to do PhD with that one, it is very difficult for you. So what you can do is some of the novelties you can add. You can make a composite filaments, like you can mix the PLA with respect to copper, stainless steel, 17.4 pH, titanium, inconel, because nowadays particles are much abundantly available. So you can mix these things and you can get a customized filaments. Okay, these filaments, if you want to purchase from other countries, for example, from European countries, as well as from, if you are purchasing from like US, one 500 grams or 750 grams will cost you almost all 30 to 40,000 rupees. So whereas if you can get your particles, if you can get the particles of the polymers, particles of the metals, we can extract the filament as per your requirements and we can give you at very, very economical price. If you bring your raw materials, we won't charge, we just charge for the machine charges. Otherwise, if you want directly filament from us, if you specify what is the composition, we can make a customized filaments and we can give you, so that you do the 3D printing of this composite and you can publish. And it is very easy for you to publish because you are using your own compositions. Next one is ball milling. Sometimes you give particles, those particles may not be accessible to us, so we try to make the particles very small, and that for that purpose ball milling is there. Then we have 3D ceramic printers, then spray nozzles and DMG Mori milling and lathe, and we have a sophisticated machine, metal 3D printer EOS M290, which is currently treated as one of the best machines of 3D printer, and you can print any type of materials, which we have a library about 20 to 22 materials. Then we have a tribometer where you can measure tribology, and as I was telling you about a viridium, we have very sophisticated viridium charmilis. Nearby you don't get all these facilities. So, in nutshell, we have at IIT Tirupati metal-based WAM is there, wire arc additive manufacturing, laser powder bed fusion is there, ceramic 3D printings are there, polymer 3D printing is there, composite 3D printing is there. We are nowadays printing carbon fibers, we are printing CNTs based also. Post processing equipment is there, 3D surface profilometer from Bruker is there, wire EDM from Charmelis Agile, DMG Mori lathe and milling machine is there, high speed cameras and IR cameras. So whenever you are doing process, you need to capture what is going on, the physics. If I want to show, if I want to explain to the paper, you require high speed imaging of the particular process. IR camera, if you have temperature dependence and other things is there, infrared camera you can use. Micro nano indenter, measuring the hardness using a macro indenter. What will happen? It will fall on a large area. When you fall on a large area, what the basic fundamental problem is that lot of voids may be there, lot of impurities will be there and other things. That's why I need to exactly understand what is the hardness of that particular material. In that circumstances, I need to go for nano size indentation, so that what will happen, I can do on a set of atoms. That means that porosity, inclusions, imperfections and other things can be eliminated most. So XRD, X-ray diffraction is there, where we can measure this n lambda equal to 2t sin theta. From there you can measure. CMM, coordinate measurement measuring is there, out of roundness tester. We have two systems for semiconductor applications, which I am not going to, which I am not talking, which is called PVD, physical vapor deposition systems we have in our institute. One is RF magnetron sputtering, radio frequency based magnetron sputtering is there. For example, if I want to coat any nano coat on my silicon substrates, I can coat. Another one is DC, pulsating DC sputtering is there. These two are predominantly used for semiconductor applications. If you have some other lecture or something, it itself is a very big lecture. Tribometer, we can do tribology and other things. 3D filaments, manufacturing unit, which is a very expensive materials you can print, or very expensive things that you can do at economic. Only thing is that you just come up with your compositions, and if we don't have compositions, you can bring your compositions to micro machining center, laser micro machining center, where you can do laser texturing, laser polishing, laser machining, laser additive manufacturing, so on. EDM, which is yet to come, Sparkonics. FESM, which we recently added. FESM stands for Field Enhanced Scanning Electron Microscopy. It has EBSD, electron beam scattered, backscattered is there. EDS is there, and it is dispersive spectroscopy, and it has a STEM, so which is called for biological applications and other things. AFM, these are some of the equipments are going to come. AFM is atomic force microscopy, which I am heading that atomic force microscopy, where we can do lot of things. And PPMS, which is planned to get. PPMS stands for Physical Property Measurement System. It may be the costliest equipment that our institute may get it, because the starting price of this particular equipment starts at 10 crores, and an average system with all the functionalities, if you want to get this, maybe goes to almost all 18 crores. So this is the costliest equipment, if you, which is on the radar, which we may get soon. And XPS, and we have HRTEM, which may be a second costliest mission, which is called high resolution transmission electron microscopy, which ranges from 12 to 15 crores. LIPS, which we have already. LIPS stands for laser induced plasma breakdown plasma spectroscopy. I mean to say, what is the function of this one? I have an unknown material. For example, any material customer gives, and he says, I want to find the composition of this particular material. In that circumstances, what we try to do is we bombard the lasers, and it will releases for each and every material, it releases one different spectrum, elemental spectrum. Based on that, we can understand what is the composition. For example, we have lot of equipments which are comes from abroad, and they never tell what is the materials that made up of. Whenever the screw, nut, bolt, anything is broken, so what will happen? You have a broken pieces only. You don't know what is the material. You need to match. For that purpose, LIPS is a very good equipment. Laser induced breakdown plasma spectroscopy. Okay. So DSC, differential scanning calorimeter, TGA, DTA, and other things are there. Bioincubator, in vivo, creep fatigue, friction stir processing, and other things are there. So these are all, some of the equipments are arrived, some of the equipments are going to arrive. Now, why I told all these things? We are open for summer interns, definitely not for 2 months. So now, new education policy or national education policy says that last semester or some people have lost 1 year. So if your students are very much interested and facilities are not there, they can come, or you can come, and we are also looking for postdocs. At the same time, those people who want to do partial BTech, partial MTech, partial PhD, experimental works, our equipments are most welcome, subjected to you have to come through proper channel to the institute. Okay, so I'm very grateful that I am appointed as associate editor for Journal of Manufacturing Process. Being associate editor, which I am going to have handle complete Asia Pacific. It's a Q1 journal which has a 6.2 impact factor, and you're most welcome, but subjected to high quality because our acceptance ratio is in between 8 to 15%. That means that highly rejection ratio is there. So, what you have to understand is you have to find some new science. If somebody has used brass, I am using copper. Somebody has used copper, I am using stainless steel. Doesn't mean that it may, every paper has a journal, every journal has a paper, but not my journal. That if at all you are seriously looking at, um, if you want it any further support or something, we are more than happy to assist you. Thank you. And these are the funding agencies. As I said, I started from IIT Guwahati with 5 lakhs. Then we got Baba Atomic Research Center, BARC, about 23 lakhs. Then TSDP, Technology Development, where I got 1 crore. Then DRDL, about 75 lakhs. Then we got a big funding from DITI, which is nowadays called MITI, Ministry of Electronics and Information Technology, about 60 crores. I have 2 imprint, one with IIT Kanpur, 3 crores, and one with ISC Bangalore, about 3 crores. ACRB, about 45 lakhs. BIRAC, about 41 lakhs. CRG, SCRB, about 32 lakhs. Then I have a big project again, IGSTC, which is Indo-German Science and Technology Council, where I have 6.8 crores. IIT Tirupati about 22.5, then DRDL about 17. Then I have small projects where, because slide is insufficient, about 56 lakhs, where I have small things like IKS 15 lakhs, TARE about 20 lakhs, ISRF about 7 to 10 lakhs. Similarly, I have co-PI project about 2020, like that, and other things. Okay, we have a TIH, Technology Incubation Hub, where I'm heading one of the vertical called Precision Manufacturing. This TIH almost all 120 crores. That is one side. Currently, we have a big team, because having said the money is one side, at the same time you should have a big team. I'm just a front face. The whole hard work. This is my IIT Guwahati team. So IIT Tirupati team, we have to come up with a photo. So with this, I would like to thank you for your all the kind patience that I am disturbing your dinner. I am disturbing my dinner also. So okay. So if you have any queries, suggestions, and comments, please do let me know. Thank you.
My question was, if anyone from a triple E background,
Uh,
uh, we can get contact with you, sir.
yeah. If you want me to connect to any electrical faculty,
Yeah.
you can contact me. I can give you some references.
Thank you so much, sir. Thank you so much.
Yeah. So it's just a Non-technical support, you mean to say?
Yeah, thank you so much, sir.
Fine, fine, Professor.
Excuse me, sir.
Yeah, please go ahead.
Sir, from mechanical engineering department, nowadays, which one is this very suitable and suggested for our mechanical department funding project, sir?
Mechanical funding, you have semiconductor machine, which is 18,000 crores. So you can look at that.
Sir.
Uh, you have mostly defense. In defense, you have ARDB board where you have materials and manufacturing.
Sir.
ISRO, now ISRO basket is released already. You just check respond basket, RESPO in the respond basket, where you have lot of problems are given by the ISRO. If you can solve those problems, they will give you a good amount of money, ranges from 20 lakhs to 30 lakhs or for you. So according to that, you can make, that is called a respond basket. So you have SERB. SERB now is merged with ANRF. So you have CRG, and as I said, that IGSTC is one of the good thing in DST, Indo-German Science and Technology Council. As I said, no, we got our complete project worth about 6.8 crores. If you are targeting large, you should target the big ones. So apart from it, if you are working in biomaterials, you have two or multiple. One is DBT, Department of Biotechnology. At the same time, you have ICMR, Indian Council for Medical Research. And you also have BIRAC, Biotechnology Initiation Grants and other things. These are the things. For a, okay.
Okay, sir. In our mechanical, not for mechanical, like any relevant to the physics or supporting points for electrical department, any funding projects also comes under the same this picture, sir.
See, this CRG, these are all are nothing to do with department. Any department can apply. It is not
Okay.
department specific. For example, you say electrical. Okay, so you can make flexible electronics, na? You see, I mean, say electrical and electronics. You can make, or for example, for electrical people, you have now EVs are
Easy, sir.
EV. Many people are going with EVs, electrical vehicles. So you develop something like battery casings development or battery electrolyte development. So mechanical people have their own version. For example, you come to us once you develop the electrolyte. What is the rheological properties? Mechanical will do. So
Sir.
because charging, discharging, what is happening while charging, how much energy consumption is there, life cycle assessment, HSS is there, humanities and social sciences. They can understand about life cycle assessment of batteries, battery remanufacturing. Remanufacturing means how to dispose it of properly. These are all for HSS. EVs is a good area where India is spending a lot of money. As I came to know that you are in Anantapur, you have Kia. So
Yes,
Kia,
sir.
yeah, you just talk to Kia, they may have a lot of problems.
Sir. Okay, sir. Thank you, sir. Thank you very much for your valuable points and suggestions for us, sir.
Yeah,
Sir, good evening, sir.
tell me. Please introduce yourself and go ahead.
Sir, myself, Chandrababu, sir, coordinator of this Atal FDP, sir. Sir,
మీ ఇంట్రడక్షన్
sir,
వదిలేండి వేరే వాళ్ళకైతే
sir,
చెప్పండి.
sure, sir. Sir, we have applied a funding project to DST, sir, in 2021, sir, on biopolymer based silica for enzyme immobilization applications, sir. So still it is under review, sir. So we have in under the nano scheme
You have applied
department.
nano mission.
Yes, sir, nano mission.
How much? 5 crores.
No, sir, 20 lakhs, sir.
Nano mission is
27 lakhs, sir.
nano mission is for large amounts.
Okay,
Nano
okay, sir.
I think, see, exactly, I also don't know.
Sir.
Normally, if your range is above 2 crores or something, they will handle. Less
Okay.
than 1 crore or something, they may not handle. I don't know, but you need to cross check
Okay.
because
Okay.
you don't know, there is a poem, Vinadagunne Oru Cheppina, like that. No, so if I said you should not blindly follow, you have to know from competent authorities.
Sure, sir. Sure. Thank you, sir.
Nano machine, why you thought of applying 27 lakhs or something? You should have applied for, see, molecule, say, immobilization of something and other things, no, that come under bio also, no.
Yes, sir. Yes, sir.
So you can try for DBT, Department of Biotechnology, ICMR, BIRAC. These are all also there. Just
Okay,
one
sir.
thing is that you can see what is the format of them, what they look. See, the perspective of a mechanical engineer looking at the problem, perspective of a bio person looking at the same problem will be different.
Okay.
Okay, when you write to the DBT or something, you look as though you are a biotechnology person. You
Sure,
write
sir.
your problem from that angle. See, for
Okay, sir.
example, I will tell you, like if
Sir.
you want to do lathe process, simple lathe turning process. Okay, what you do? You just do lathe turning process, makes the forces, FR, FA, all the things under the axial force, radial force, cutting force, and so all things. But the same thing, if you look at chemical composition of the cutting fluid, interaction signs of the cutting fluid at elevated temperature of the material chip, and you can see the perspective is different, but the output is approximately same. Am I right?
Yes, sir.
So case one, you may not get very good publication, maybe. Case two, you may get very good publication. That's how the process is same, but the thing is that आपका सोच बदलना चाहिए. आई डोंट नो, मे बी सम पीपल, मे बी हिंदी पीपल. सो
Yes,
आपका
sir.
सोच का नजरिया बदलना चाहिए, और आपका किस डायरेक्शन से मुझे ये चीज को अटैक करना चाहिए ताकि मेरे को पब्लिकेशंस मिले या अदर मिले. ओके, सो दैट्स व्हाट. सो मैं हिंदी में इसलिए बात कर रहा हूँ कि कुछ लोग हिंदी वाले होंगे, उसको भी मुझे रेस्पेक्ट करना है.
Yes, sir. Yes, sir.
We can understand, sir.
Thank you, sir.
थैंक यू जी. Okay. So thank
Sir, no,
you, Chandrababu ji, and thank you, Kiran ji, for
Sir, thank you.
at
Thank
the
you,
same
sir.
time at the outset, I would like to say PVKK Institute totally. Okay.
so thank you, Dr. Ravi Shankar, sir, for your informative talk and for being with us instead of your busy schedule. We know how busy you are, but still you have made your time available for us and joined us, though late, but your session was very informative, and the information what you have shown through the videos and the pictures was more elaborative in nature. So it was very crystal clear. So thank you. And also thank you for sharing the research facilities, what is existing in IIT Tirupati, because most of the people are from Andhra Pradesh, they could avail these facilities. And we are also happy to know that the arrival facilities which are going to come soon, so that it could be very helpful for researchers like us, sir. Thank you for your time, and thank you for your patience, and thank you for your valuable insights. Thank you, sir.
Thank you, ji. Okay. So thank you all, and I have to leave to some other meeting also. Okay. Thank you.
Thank you, sir.
Okay. So those people who want to interact with me, you can get my details from organizers and they can interact. Okay. So thank you all, and have a nice time ahead.
Thank you. Thank
Thank
you.
you so much.